This was in IK's award with Johnson Massey, and we were looking at structure activity and in particular the effects of aging on three-way catalysts. I'm now a postdoc with Professor Andy Beale at UCL and soon to be research fellow, which I'll talk about a bit later. And this is I'm working on the Laurelin project, which is looking at novel reactor technologies, including non-thermal plasma, magnetic induction, and microwave heating as alternatives to conventional heating for CO2 conversion to methanol. The work that I'm going to be talking about today was mostly from my PhD with Dr. Emma Gibson and some that we've done since, kind of continuing the project. And I'm going to start by introducing three-way catalysis and the material Ceria Zirconia, and then talk about two kind of interesting aspects of it and showing you some results from these, and then discussing what's coming next. So to begin, you're all probably most familiar with three-way catalysts, being that they are the catalytic converters in petrol engines. So in petrol engines, the air-to-fuel ratio is 14.7 to 1, and three-way catalysts are designed to work under this regime. So they comprise of a honeycomb monolith structure, and the catalytic components are suspended in the wash coat. It's quite a tricky technology because they must be able to catalyze both the oxidation and the reduction reactions in order to remove the CO, the NOx, and the hydrocarbons. Ceria Zirconia itself is used because it's an oxygen storage material, and that is a really important promoter to the three-way catalyst. And in fact, the majority of research that is done on three-way catalyst focuses on this material because it's the really crucial one in getting that high performance. That's because it has these removable lattice oxygens. So, let me just put my pointer on. So these yellow and green spheres represent either a zirconium cation or a cerium cation, and the oxygens are red. And you can remove up to 25% of oxygens from a 50-50 Ceria Zirconia structure. And this happens concurrently with the reduction of cerium 4 to cerium 3. And this oxygen removal is so crucial because it means that when your exhaust is running in low oxygen concentration environments, it can provide additional oxygen to make sure that all of the CO and the hydrocarbons can be oxidized. And similarly, for the NOx reduction, if there's too much oxygen in the exhaust, it can take in some of the oxygen. And this really widens the operational window at which these three-way catalysts can operate. It's also just a really good support material for the active catalyst, which is palladium. Well, palladium in this case, but can also be rhodium or platinum. Oh, is it working? A major downside, however, to the Ceria Zirconia that I just talked about, the 50-50, is that it is not very thermally stable. So it stabilizes in the structure I just showed on the previous slide. It's called a pseudo-cubic phase. It's more like, as labeled here, a nanocomposite mixture of cubic and tetragonal phases. But you can see that this is by in situ powder diffraction over time at high temperature. So here this is 950 degrees. You get phase separation into a Ceria-rich cubic phase and a zirconia-rich tetragonal phase. And that is because these are the two different symmetry of structures that Ceria and zirconia would each stabilize into if they weren't mixed in a cubic phase. So for this reason, most commercial formulations include rare earth dopants. And in this material we're using, it's a Johnson Massey commercial catalyst formulation, we have lanthanum and neodymium. And just the addition of really tiny amounts of these dopants can prevent the phase separation under the equivalent conditions. However, structure affects performance. So if we look at the oxygen storage capacities, we see that for the bare Ceria Zirconias, the doped is improved over the undoped. So the units that we're reporting here are also important. It's percentage utilization. And that's because if we want to compare how much we can reduce each of these structures, well, looking at our formulations up here, one of them has less cerium than the other. And we need to be able to reduce the cerium to remove the oxygen. So if we just compared the kind of raw data, it wouldn't really be a fair comparison. So we use percentage utilization because it allows us to normalize to the amount of cerium. So instead, we're talking about of the theoretical maximum oxygen that can be removed, how much is being removed. So for the bare Ceria Zirconias, as I said, the dope material has a slight performance increase, and that's because whilst cerium and zirconium in their oxidized form are in 4+ oxidation states, the rare earth metals are 3+, and this means we have oxygen vacancies in the structure. This doesn't mean that we can remove and replace more oxygen because of these vacancies, but they are fixed vacancies, and it means that the oxygen that is being removed can diffuse much more easily through the structure. However, we don't use bare Ceria zirconia, we use platinum group metal doped Ceria zirconia. So when we look now at the same material but with palladium on, suddenly our undoped material has a huge advantage and it performs much more superior. Similarly, if we look at the catalyst performance by its activity, so we tested CO conversion, NOx conversion, and hydrocarbon conversion all under exhaust gas mixtures, we see again that our undoped material performs better. It has a lower light-off temperature and reaches higher maximum conversions. We also have this unusual feature for the doped material, where we have this kind of activation period that's required before the conversion can proceed. However, the doped material and the undoped material are structurally very similar, where they both stabilize in the same cubic phase. They both have very similar surface areas and they both have very similar crystallite sizes. So the difference in the two must be in between the Ceria zirconia itself and its interaction with the palladium. And we know that this interaction is really important because, for example, here is a study that was done by Nagasawa in 2023. This shows an image where this is a Ceria zirconia and these are palladium nanoparticles. And they reduced the structure and then they exposed it to labeled oxygen, so oxygen 18. And this shows how much the oxygen 18, the concentration of it and the diffusion of it into the Ceria zirconia in an area that's surrounding palladium nanoparticles compared to an area that isn't. And you can see how much the palladium, being in proximity to palladium, improves the oxygen diffusion. The reason for this is because there is a redox couple at the interface between the cerium, which is cycling 3+, 4+, and the palladium, which is cycling metal and 2+. So when oxygen is removed, it diffuses from the bulk to the surface, and then it's released from the surface at the cerium-palladium interface via these redox mechanisms. And that's really crucial, and it really allows a lot more oxygen to be released once it's diffused to the surface. And once you remove more oxygen from the surface, you increase the concentration gradient, so you drive more oxygen to move from the bulk to the surface. So knowing how important this interface is and seeing the difference in conversion between our doped and undoped catalysts, we want to look into this more and see if this is the reason why the behavior is so different. And we figured that we can use this palladium redox mechanism to infer the strength of the metal support interaction. So palladium oxide thermally decomposes to palladium metal at temperatures above 850 degrees. This will happen even in the presence of oxygen. That's just the temperature at which palladium oxide becomes less favorable than palladium metal. And it will reoxidize, so reversibly reoxidize back to palladium oxide at temperatures below 750. So we're going to use this equilibrium and drive it back and forth to see the kind of redox chemistry of palladium on the two different Ceria zirconias. So in this in situ powder diffraction, we are cycling to force palladium metal and then force it to go back to palladium oxide and cycle back and forward between the two. If we look at the results for the undoped material, so this is just palladium on the 50-50 Ceria zirconia, we see reflections from palladium metal present at high temperatures, and then some very small broad reflections from palladium oxide present at low temperatures. But crucially, we have some palladium metal left over at the lower temperatures. If we compare this now to the doped material, you see the absence of any reflections here, meaning that apparently all of our palladium metal has reoxidized at this lower temperature. What can we infer from this? Well, the reoxidation of palladium metal present as large metallic nanoparticles to the oxide requires the redispersion of nanoparticles, and that's quite well known in the literature. You oxidize the surface of the nanoparticle, the small oxidic part kind of migrates away over the surface, exposing more metal to oxidize that. So if this redispersion is less able to happen on the undoped material, it implies that the nanoparticles are more anchored, and that tells us we have a stronger metal support interaction. We can track the crystallite size of the palladium metal, so from these sharp reflections here, over the cycles. And another interesting effect we observe is that even after we reoxidize the majority or all of our palladium back to palladium oxide, which is dispersed over the surface, when we heat it up again and cycle again, the palladium continues to grow, as you see here, from the temperature it achieved during the previous cycle. So we have this memory effect going on. one question that this led to is all of our palladium metal really oxidizing them, particularly on the rare earth dope material here, where we have no palladium metal reflections at the lower temperature? Does that mean that we've oxidized all our palladium, or is the palladium metal which is left too dispersed or insufficiently crystalline to be visible by powder diffraction? So we repeated one temperature cycle. So this is just one of our temperature cycles in the powder diffraction using X-ray absorption spectroscopy. And this was on B18 with Veronica as our local contact. So we started with 100% palladium oxide at room temperature. We increased the temperature through 650 up to 950 degrees. Wait 2 hours as we did in our XRD cycling, and then cool it back down. We start to achieve palladium metal as we expect by the 950 mark, and after 2 hours we have fully palladium metal, which then reoxidizes during the cooling. Two things to note here is that firstly, the data is in agreement with our XRD that the reoxidation is enhanced on the doped Ceria zirconia. You see we have a higher fraction of palladium oxide. But also we do have palladium metal left in both materials after the cycling. So particularly for the rare earth dope material, there are things that we're missing with powder diffraction. There is 31% of metal there, which we're not seeing. And that could link to our memory effect and to why the redispersion isn't complete and why it can grow from the same place it was in the previous cycle. If we now highlight this 2-hour period at 950 degrees and watch the reduction from kind of this point to this point, looking at the fraction of palladium metal, we see that the reduction of palladium oxide is much faster on our doped Ceria zirconia, which again confirms this weakened metal support interaction where the palladium nanoparticles are more mobile and less anchored and therefore easier to reduce. So to summarize this part on metal support interaction, yes, these materials are doped because it increases the thermal stability. That means we improve the lifetime of the catalyst, and also means we can widen our operational window because the temperatures which three-way catalysts are exposed to can vary from 100 degrees when you first turn on your car to up to 900 degrees during really harsh acceleration events. So if we need the material to be able to respond quickly to these changing temperatures, and on the rare earth dope material, the palladium can fully reoxidize or reoxidize more and then back, then that seems like an advantage. However, the trade-off is that we're weakening our metal support interaction. And looking back to our oxygen storage and activity data, that weaker metal support interaction means that redox couple is not acting, not being as beneficial as it could be. So we're losing less oxygen from the material, and that corresponds directly to our conversion data because oxygen storage is really crucial for CO conversion when oxygen concentrations are low. It also explains why we have this activation, because when we start the CO conversion, we believe that the part of the catalyst that's doing most of the work is just the palladium. And it's only after this kind of activation period under slightly reducing conditions at 200 when the kind of oxygen is able to be released from the Ceria zirconia via the palladium in that kind of redox couple mechanism. So after that point, we're able to operate in this Mars van Crevelen mechanism. Is it worth the trade-off then if we're sacrificing performance and oxygen storage? Well, another part of the project was aging the catalysts. And if we just look at what happens to the oxygen storage after aging, the blue is the doped material, which after 12 hours at 950 degrees retains all of its high temperature oxygen storage ability, whereas the undoped material loses it across all regimes. Oops, so yes, the trade-off is still worth it simply for the lifetime of the catalysts. So I've talked a lot about the removal of oxygen from the surface via the interface and how that correlates with the activity in the palladium redox. But thinking now about the actual bulk structure of Ceria zirconia and what happens to it during this. Well, I said that we can remove up to 25% of these oxygens. In pure Ceria, without any zirconium there, you would only be able to remove around 10% of the oxygens. But they are isostructural. So the structure of pure Ceria looks almost identical to the structure of Ceria zirconia. So what's happening to the structure when we remove all of these additional oxygens, especially given that we've said that Ceria zirconia is only really metastable. Predictions from the literature, from particularly powder diffraction, ex situ powder diffraction, and DFT, is that firstly, the oxygen which is removed from the structure is only at the interface between a cerium and a zirconium. Secondly, the zirconium is not reduced, and that kind of fits with zirconium's behavior, but the number of neighboring oxygens decreases. And when this happens, we get non-uniform zirconium-oxygen bonds. So all of these studies that I've referenced at the bottom, you'll notice are from 20 or more years ago. We now have much better facilities and are able to kind of look into this more operando. So we wanted to see, can we prove any of this and with an operando experiment? So for this, we went to the XMS beamline, which is the UK CRG beamline at the ESRF. This work was done with Paul Thompson, and he's been really instrumental at helping us prepare for and perform some complex experiments. We wanted to go to XMS in particular because, unlike the beamlines, for example, here at Diamond, we can measure both the cerium L3 edge and the cerium K-edge. So we can obtain both a more Zane sensitive edge and a more XAS sensitive edge. We can also measure the zirconium K-edge, the powder diffraction, and have a mass spec monitoring the experiment at the same time. This is the reaction profile, so the regime that we followed. We increased the temperature. We cycled between the two states, the reducing and oxidizing state, a while first to clean the surface and kind of get the material moving. And then we left it under carbon monoxide and then left it under oxygen. So looking first at the cerium L3 edge, this is a more popular edge to measure. It's very Zane sensitive, but you can't get the XAS. So we were using it just to confirm that the reduction was in fact happening. And we can see that at 200 degrees, when we switch to CO, we have 42% cerium 3. And then when we oxidize the sample again, we go back to 100% cerium 4. So this is a reversible process. We could also confirm this with the mass spec. So when we turn on the CO, we have a small delay in the CO reaching the mass spec because it's being consumed in the conversion to CO2 using lattice oxygen. And we can see this spike in the CO2 here as well. And just to note, again, this is happening in the absence of oxygen. So the oxygen here is coming from the material itself. Looking at the powder diffraction, we don't see any obvious structural changes during the entire experiment. We see the emergence and disappearance of palladium metal as we put it under reducing and then oxidizing conditions. But kind of focusing in on one of these reflections, we don't see any change to the peak shape, which might imply a loss of symmetry, no extra reflections. We just see peak shifting as the lattice contracts as it loses oxygen. Looking at the cerium K-edge, the Zanes doesn't tell us too much other than that a reduction is occurring, but looking at the XAS, we now see this decrease in amplitude here, which tells us that we're losing oxygens from the first coordination sphere. And we also see some changes going on in the Fourier transform for the second shell, which I'll explain in a minute, but we're looking into a bit more. But so far, none of this seems to indicate a deviation from pure Ceria. We have a cubic material that is not changing symmetry, is just losing oxygen and then regaining it, until we get to the zirconium K-edge. So this is the spectra at 200 degrees in helium, and this is at 200 degrees in CO. And these changes seem very small, but they are significant. They're also reversible, so when we put the oxygen on again, we go back to our initial state. Looking at the literature and comparing to standards, we see that this transition here is really indicative of a cubic to tetragonal transition. So we have local disorder around the zirconium in terms of zirconium oxygen bond lengths changing and becoming less equal, and like a symmetry loss, very localized, but on the macro scale, for example, by powder diffraction, the symmetry of the material is retained. And this is what's been predicted by DFT over 20 years ago, but hasn't been shown yet. We can see this also in the K space. If we compare to standards, we see this cubic to tetragonal transition here. But these changes are quite small, and if we want to really dig into what's happening to the structure, we need to see if we can amplify them. So if we increase the temperature, we'll remove more oxygen from the material, but our excess will become significantly worse. So we move to the kappa phase material. So this is the exact same material, 50-50 series zirconium with oxygen, but it's gone through a high temperature redox treatment, which improves the ordering and doubles the unit cell size, which you can see here. What this change does then is, in our Ceria zirconia material I was just talking about before, we have domains of Ceria-rich material and domains of zirconia-rich material linked by these oxygens at the interface, and these are the ones that it's believed that are removed. But after this treatment to form the kappa phase, we alternate exactly cerium, zirconium, oxygen, sorry, cerium, zirconium, cerium, zirconium, and that massively improves our oxygen storage capacity. So comparing here the kappa phase in blue with the material that we were looking at just a minute ago in red. You might be wondering then why this isn't the commercial material for three-way catalysts, and it's because you significantly lower the surface area by doing this treatment, and the material is unstable above 800 degrees. So just to show you then that these were the figures I just showed with the original Ceria zirconia material, and these are the changes instead that we see with our kappa phase, and particularly in case base here, you can see a really significant cubic to tetragonal transition. In the Fourier transform, in the second shell, these materials are quite difficult, and it's very difficult to assign all of this, particularly because the cerium paths and the zirconium paths are completely destructive. So we're losing a huge amount of intensity here. So we're now working with modelers from Diamond Light Source, and they are generating some structures that this material could be sitting in under the different conditions, which we can then apply to our data. Just to finish off, so I have been awarded a IChemE research fellowship entitled Driving Catalyst Scale-Up with 3D Diffraction. The aim is to be able to do XRD CT, so three-dimensional XRD, on an intact monolith during operation. From this, build up a picture of what the catalyst looks like during operation for something even 10 centimeters big. And then from each pixel of this image, this CT-like image, we'll be able to pull out a diffraction pattern. And this will really help with the scale up to understand what's happening inside the monolith, at what point in the channels, at what point in height. And the application of these catalysts is for LNG carriers, so in the maritime industry. And I'd just like to acknowledge everybody in this slide, in particular those who have pictures from Glasgow, ISRF and JM, and obviously my supervisor through this work, Dr. Emma Gibson. And thank you very much for listening.
Thank you very much, Lucy, for a really excellent and clear talk. Are there any questions for Lucy? If so, please type them in the chat. I have a question, and it may be horribly mean, I'm not sure, but it's something I've been curious about. With the government's push for electrification with these three-way catalysts, are there any other applications?
Not really. However, there are large sectors where electrification is not going to work. So, for example, primarily shipping. Those don't use three-way catalysts like this, because they're diesel engines, but they're similar. They also use Ceria zirconia, similar formulations. So, yeah, there are areas that it's just not going to be possible to electrify. So it is still worth continuing the development of these materials. And again, it's going to be over 10 years until a legislation comes in that all cars have to be, battery cars. And in the meantime, we just stop improving the catalyst. So I feel quite strongly that it's still worth doing. But yes, eventually they will be obsolete, hopefully.
Sorry, I wasn't questioning the validity of the research. I was hoping that the effort that went in could go somewhere else.
Yeah. It's quite funny because my husband does battery materials for electric cars, so it's a common argument between us.
Okay. Well, I think your talk was so clear that I'm not getting any questions in the Q&A.
It's fine. I'll take that.
No, I mean, it was a really excellent talk, and as a non-practicing scientist, I understood it. So thank you very much.